Good morning, team. It's been a while since I made a video for class. Haven't done that since last year at the beginning of the pandemic. Today's goal is going to be to draw a divergent continental boundary, but instead of showing what happens in the first 0 to about 20 million years, we want to see what happens if this process continues. Quick review of the divergent continental boundary. This happens when we get a mantle plume, a mantle current that's moving upwards really hard towards the surface. And as that mantle plume hits the underside of the crust, it spreads out, which causes the crust to stretch. As the crust stretches, it breaks into a region of basins and ranges. You can see this across Nevada as the basin and range formation. If this process continues, gradually it will cause the continent to stretch out like silly putty until eventually the continent snaps in half. And I want to show what happens with that process. What happens if the divergence continues? This is what caused Africa and South America to separate. This is what is gradually stretching out the United States. This is why East Africa is going to peace out and cruise up towards Saudi Arabia. So here we go. So first off, colors. I have my black pen. I have a blue, and I know that the blue is a little difficult to distinguish from the black on the webcam. So I will always make sure to say when I'm using blue versus black. I've got a red for when things are hot. And I've got a green as an accent color for a little bit of labeling. The green is also a little bit tricky to tell, so I'll make sure to mention when I'm using it. So go ahead and get your colors ready. Slide down to the bottom half of this diagram where we folded and can continue down below. And let's go ahead and get started. So with my black, I'm going to label this that I'm drawing a divergent continental boundary past 20 million years. Divergent continental boundary. So this is what happens roughly 20 million years on. This is a pretty rough estimate, but it does the job. So divergent continental boundary, 20 plus million years going on. And remember, our divergent means to separate. Starting on Wednesday, we'll be tackling convergent boundaries. And if divergent means to separate, I imagine you can guess that converge means to come together. All right. So using my black pen, I'm going to make a few reference marks for this drawing. So if I think about my vertical space, I'm going to make a couple of marks a little bit above and a little bit below the halfway line. Not a whole lot is going to end up being drawn above this mark. So you can tend towards the top of the page. And then same thing on the other side, kind of mark. I've got a couple inches down below. I've got about an inch, inch and a half up above. These are going to be the edges of our continental crust. And we're going to go ahead and draw that continental crust in. So at first, it looks really similar to our big, fat continental crust on the sides in our divergent continental boundary in the early days. But you'll notice that there's a really big difference as we get towards the middle. So I'm going to come in about a quarter of the way towards the center on both sides. So leaving this middle area totally blank for now. I'm going to come in on one side, and then I'm going to kind of narrow up. And this is a pretty abrupt narrowing. So this is not like a long, graceful curve. It's a pretty, like, about face. And then with the continental crust, remember that we had that bumpy basin and range surface kind of right next to where the crust was stretching. So that's still there. We've got that bumpy kind of range, basin. But as I get towards where I narrowed up on the underside, I'm going to do the same on the top, and I'm going to come down. I'm going to come down kind of like that. I'm going to mirror this onto the opposite side. So I've got my range and basin and range and basin and range and basin. And then I'm coming down. And then same thing, the underside's pretty easy. Just flat and up. There we go. It's like two lobsters, or one lobster pinching his claws. So this is the continental crust. This would be analogous over here. This is like this region. And then over here, we've got this region of the continental crust. But in the middle here, where we have this crust thinning and extending, something new happens. Before we get to what happens, let's quickly label. So still using my black, I have the continental crust. Which is, of course, made out of granite, mostly. And same thing on the far side, continental crust, which is made of granite. In the middle, though, something very strange will happen. So as that mantle material stretches our crust, eventually the crust stretches to the extent that it snaps. And when crust snaps, mantle material is able to break through. And we know what happens when mantle material breaks through. When mantle material breaks through, it'll harden and it will become new basalt seafloor. So I'm going to come in from both sides towards the center, and then I'm going to do these little kind of projections coming up and then go back over. And what I'm drawing here is brand new basalt oceanic crust. This is going to start to look really familiar, I hope. So more labeling is important. This right here is brand new, beautiful, new oceanic crust. And this is forming because of the mantle action. Let's go ahead and label the mantle. Switching to red. Oops. Switching to red. I'm going to label the mantle down below. It's huge, so I use big, bold letters. It's hot, so I use red. And since this is a divergent boundary, those currents are doing the same thing they were doing before. They're coming up in the middle of the extension and then moving sideways until they eventually get cold and fall back down. So we're going to see that same sort of behavior here. We've got mantle material going up, and I'm going to send it through this crack, but not above. And then I'm also going to show that in addition to breaking through the crust, this mantle material spreads sideways. Eventually, the mantle material will cool off. It gives a lot of its heat to the underside of the crust. And as it cools off, switching to blue, as it cools off, it will sink back down into the mantle. This is in blue to show that our mantle material is getting cold and eventually sinking back down, where it will get hot and pop back up and then get cold and sink back down because we have a cyclical convection current. And of course, if the mantle is spreading apart, then our plates are also going to spread apart. I'm switching to green to label the plate motion. This is my accent color, so whatever you want to use, like a yellow or an orange or a bright purple, doesn't matter. It's just an accent. Just want something that pops. I'm going to label that plate motion. And because the mantle's going to the right here, the plate will also go to the right, because the plates will only ever do what the mantle does. Same thing on the left. I have plate motion. And that plate on the left is spreading apart because the mantle currents are spreading apart. Okay. Well, let's say some water hits this new low point. This is going to be a lot lower than the continental crust because the basalt forms and then it seals up quickly. And so this is going to end up getting covered in a layer of ocean. This is my blue to show that this is water. This is a new ocean, which is kind of exciting. We have a new ocean. If you want to see this in progress, you can check out the Red Sea. The Red Sea is a brand new ocean, or, well, the beginning is a brand new ocean. You can look at the Gulf of California between Baja and Mexico. That just opened up about 15 million years ago, and there's a new sea forming in there, the Sea of Cortez. All right, a couple of little labels to toss in and a couple of additional details to fill out. So, of course, where our mantle material is breaking through this new oceanic crust, it's going to cool off. So this is still my blue, showing that mantle material cooling off. And then switching to black, this will make a mid-ocean ridge. And hopefully you've noticed that this looks awfully familiar because this is really just our divergent oceanic boundary diagram, but like a little tiny version. This is where oceans come from. If you have a divergent boundary that rips a continent open, it will split the granite, form new basalt, and make a new ocean basin. And so, a neat little plot twist with our divergent continental boundary is that it will, this is my accent color in green, it will become a new divergent oceanic boundary. Because that's really what this is at this point. Since what's splitting now is not the continent stretching, but it's the ocean spreading out, this isn't really a divergent continental boundary anymore. It's the evolution of a continent that has split in half. A few last things to label using my green labeling color. So on either side here, we have new coastlines. Coastlines that did not exist before. So this is like the west coast of Africa or the east coast of South America. Neither of those coasts existed when both land masses were pushed together as part of Pangaea. But as they separate, you get two new coastlines, which is kind of neat. So this is a new coastline. This, of course, we know the name for this feature. This like ridge of basalt rock that forms in the mid-ocean is, of course, the mid-ocean ridge. This is a new mid-ocean ridge. And this continent here, or this one over here, they're going to be pushed passively away. And as they move, it's not going to be a very active region on this coastline. A good example is the east coast of the United States. Kind of picture the mid-Atlantic ridge, and as the mid-Atlantic splits open, it's pushing Africa on one side and Europe on one side, and then South America and North America on the opposite side. But on that east coast of North America, not a lot's going on geologically. There's really very few earthquakes, very few tsunamis in the Atlantic Ocean. In fact, virtually zero tsunamis in the Atlantic Ocean. So this is what we call a passive continental margin. Contrast that with the west coast of North America, where we live. We are on an active continental margin. All kinds of crazy geology is happening over by us. But if we have a divergent continental boundary that splits and becomes a new ocean, those continental edges are going to be chill. So we call this a passive continental margin. If you really don't like earthquakes, you can go live on the east coast of the United States, and there aren't any, and you will be just fine. I think that's about it. Only last thing that we haven't labeled is, of course, our new oceanic crust is made of basalt. So let's label this new basalt. And we're done. That's it. I'm going to go ahead and make my ocean a little more oceany while you finish off your last details. But that is our diagram. Tomorrow in class, if you are an in-person student, I'm going to ask you to show me your diagram for credit. If you are a Zoomie, you can submit it online, or you can show me during class tomorrow by holding it up to your camera. Either way is totally fine. And of course, as always, have good days, be good people, and I will see you in the future.